Hi, I will talk about the category of M-sets for M monoid and its topos-theoretic properties. If you have any questions or comment afterwards, please send me an email. My current email address is here. So this will be based on two papers, mainly the second one, monoid properties as invariants of toposes of monoid actions, and the second paper is joint work with Morgan Rogers from the University of Insubria in Como. For me, a monoid is not necessarily commutative, so it's a set together with an associative multiplication law and a unit 1. And similarly to the case of groups, you can define what the right action is of a monoid on a set, and you can define morphisms between two right M sets. So why would you study monoids? Groups describe symmetries of mathematical objects, and monoids describe self-maps of mathematical objects, so maps from an object to itself that preserve some structure. And here are some examples of monoids. For example, the natural numbers under addition. This is a free monoid with one generator, the number 1 in this case. Or you can look at the natural numbers under multiplication. This is a free commutative monoid with as generators the prime numbers. And one very complicated monoid is the monoid of ring endomorphisms of the polynomial ring in 3 variables over the complex numbers. Another example are the 2 times 2 matrices with integer coefficients under matrix multiplication. So how do you construct new monoids? If you start with a group, then there's a bijection between partial orders on this group that are compatible with group multiplication and submonoids of this group. So how does this work? If you have a partial order on the group, then you can construct a monoid by taking the elements that are bigger than the identity element of the group. And if you already have a monoid, then you can define a partial order using the division relation. So A is smaller than B if there is some M in the monoid M, such that B is equal to A times M. And in this way, you can recover, for example, the natural numbers under addition from the group of integers together with its standard partial order. So when precisely can a monoid be written as a submonoid of a group? At least the monoid should be cancellative on both sides, and for commutative monoids this is enough. But for non-commutative monoids you need something more. For example, the right OR condition. And this right OR condition is sufficient, so every cancellative monoid that satisfies the right OR condition can be emitted into a group, but it's not necessary. For example, the free monoid on 2 generators, this can be emitted into a group, the free group on 2 generators, but it does not satisfy the right OR condition. And we want to look at a fixed monoid M and the sets together with an M action. And we want to look at these sets in a geometric way. So here are some drawings of 4 sets together with an action of the natural numbers under addition. So we have the trivial set, we have the n action on the set with 2 elements that is given by addition modulo 2, the n action on a set of 3 elements with action given by addition modulo 3, and here you have another action on a set with 2 elements 0 and 1, and 0 is sent to 1 while 1 is sent to itself. So using these drawings, you see that there is some analogy with covering spaces in topology. So you start with maybe the trivial set as a base space, and the other examples are locally trivial, so to speak, over this base space. How to make this precise? We can look at the monoid M as a category with one object, and as morphisms of the category, you take the elements of the monoid M. And using this interpretation, there's an equivalence between sets S with the right M action and functors pi from a category C to the category M. And these functors should be local homeomorphisms in the sense that this pi is a bijection between morphisms with codomain C and morphisms with codomain pi of C for all objects C of this category C. So this is another way of looking at sets with the right M action. And another way which is equivalent is taking pre-sheaves on a monoid M. So the second way of looking at it is sometimes called discrete op vibrations. So now for a more precise statement, we take the first category to be the category of sheaves on a topological space X. And here sheaf is another word for a local homeomorphism. And the second category is the category of equivariant sheaves on a topological space. So these are sheaves, but they take into account the action of a group G on the base space X. And then the third category is the category of pre-sheaves on the monoid M, or in other words, the category of sets with the right M action. And then what you can do is, if you have a submonoid M of a group G, then you can construct a space X with a G action such that the category of pre-sheaves on M is equivalent to the category of equivariant sheaves on X with this G action. And this theorem follows directly from what is called the comparison lemma in topos theory. So this is a way of, if you have a monoid M, which is embedded into a group, to give a geometric interpretation to the M sets. So what about if the monoid does not embed into a group? For example, if the monoid has idempotence or is not cancellative, for example. Well, we can treat a general monoid M as a space by looking at this category of M sets. And the reason this works well is because this category of pre-sheaves is what is called a Grothendieck topos. The definition of a Grothendieck topos is here. A Grothendieck topos is a category equivalent to the category of sheaves on a small category C equipped with a Grothendieck topology J. So in particular, pre-sheaves are a Grothendieck topos by taking the trivial topology. And Grothendieck toposes have various properties. For example, they have all colimits and limits. You can look at functions between these Grothendieck toposes. And the right notion of function is a geometric morphism in this case. So what is a geometric morphism from E to E prime? This is a functor in the other direction that preserves colimits and finite limits. And this functor we call the inverse image functor, and it automatically has a right adjoint that we call the direct image functor. And as an example of geometric morphism, every Grothendieck topos E has a unique geometric morphism to set. And this is called the global sections geometric morphism. So why is this the right notion of morphism? Well, if we look at sober topological spaces, for example, Hausdorff spaces are sober, then there's a bijection between geometric morphisms of the sheaf toposes and continuous maps between the topological spaces. Similarly, for monoids M and N, there's a bijection between geometric morphisms from one topos to the other, and sets Y that have a compatible left N action and right M action, such that the left N action is flat. Here, in this case, the inverse image functor is given by tensoring on the right with Y over M, and flatness expresses that this inverse image functor preserves finite limits, similarly to how flatness in algebraic geometry also says something about preserving short exact sequences. So what does the global sections geometric morphism look like in our case? So, for example, if you start with the set S, then the inverse image functor sends this set S to itself, but with the trivial M action. And in the other direction, if you have a set X with an M action, then the direct image functor sends this M set to the set of fixed points. There's also a left adjoint to the inverse image functor, and because this left adjoint exists, we say that the topos is locally connected. And what does this left adjoint look like? Well, you can define an equivalence relation on the elements of the M set by saying that two elements are equivalent if there is an element M of the monoid that sends one element to the other. So in some sense, the equivalence clauses for this equivalence relation are precisely the connected components of the M set. So this is why these gamma lower shriek will also be called the connected components functor. So now some more algebraic terminology. An element of the monoid is called right absorbing if it absorbs elements on its right, and it's called left absorbing if it absorbs elements on its left. And further, the monoid is called right collapsible if for any two elements A and B of the monoid there is an element C such that AC is equal to BC. And the monoid is called right or if for all elements A and B of the monoid there are elements R and S of the monoid such that AR is equal to BS. So we see, for example, that having a left absorbing element is stronger than being right collapsible. And in turn, right collapsible is stronger than being right or. So what Morgan Rogers and I did in our joint paper is we looked at various topos-theoretic properties in the special case of presheaves on a monoid, and we looked at what the corresponding properties of the monoid were. For example, these are properties that are related to the global sections geometric morphism, more precisely with the direct image part, which is called the global sections functor gamma. So if this functor gamma preserves all colimits, we say that the topos is local. And to get some geometric intuition, we can look at topos of sheaves on a topological space, and we can try to determine when this topos is local. And this is precisely when the topological space has a focal point. We only look at topological spaces that are sober here. And what is a focal point? A focal point is a point that has only open neighborhoods the whole space. Or in other words, it's the point that is contained in the closures of each other point. Examples of local topological spaces are, for example, the spectrum of a local ring. Another property is when gamma preserves filtered colimits. This is a bit weaker. And the corresponding topological property is that the topological space should be a spectral space, so it can be written as the spectrum of a commutative ring, or for example, a compact Hausdorff space. These are also strongly compact. And what are now the corresponding monoid properties that we found? We find that the topos is local if the monoid has a right absorbing element, and the topos is strongly compact if the monoid is right factorably finitely generated, which is slightly weaker than being finitely generated. So here are some other topos-theoretic properties related to the connected components functor C. This connected components functor only exists if the topos is locally connected, like in our case. And if this connected components functor C preserves all limits, then we say that the topos is co-local. And to get some geometric intuition, for sober topological spaces, the topos of sheaves on it is co-local if the space has an open dense point. And what we found is that for monoids, the category of presheaves on the monoid is co-local if and only if the monoid has a left absorbing element. We can look at some weaker properties as well. For example, if C preserves finite limits, then we say that the topos is totally connected. And for sober topological spaces, this corresponds to being irreducible. For example, the spectrum of a commutative ring without zero divisors. And we found that for monoids, this corresponds to the property of being right collapsible. We will give an example of a proof. So we want to prove that the connected components functor preserves equalizers if and only if the monoid is right collapsible. So this is the second row in the diagram here. So suppose that C preserves equalizers, then we can look at the particular equalizer diagram with as objects each a copy of M. So this is M with the right action given by multiplication. And we take two maps. The first map is multiplication by A on the left, and the second map is multiplication by B on the left. And because both objects have one connected component, the equalizer should also have one connected component, because the connected components functor preserves equalizers. And in particular, the equalizer should be non-empty. But because this equalizer is non-empty, we can find an element M of the monoid such that AM is equal to BM. And this shows that M is right collapsible. And in the other direction, suppose that M is right collapsible, then each right M set S defines a diagram, which is a constant diagram. So the object is the set S, and the transition maps are multiplication by M for each element M of the monoid. And if you would take the co-limit of this diagram, then you would get the set of connected components of S. And because the monoid M is right collapsible, we see that this is a filtered diagram. So the co-limit is actually a filtered co-limit. And filtered co-limits commute with finite limits. So the connected components functor commutes with finite limits, and in particular, this connected components functor C commutes with equalizers. For the other proofs, I refer to our paper. And thank you for listening. And I would also like to thank the organizers of JMRA for creating this platform. And I hope that many other people will submit videos. So, bye.